Hello guys, this is the fastest revision video of chemical technology. So this is meant only for revision purpose. So let's begin. Hope you like and share this and subscribe. Everything what that you want to do is do with the video. Okay, let's start. So first we have alternate polymers in which M like this way. Next we have block polymers in which M in one house, N in one house, again M in a straight way, and finally we have graph polymers. Graph polymers means N, and here in the sideways we have M house, M house. Okay, in this way polymers. And next we have isotactic means iso means they on the same side. Okay, so let's say this is a polymer and B is some compound, it's on the same side, iso. Okay, if it is alternate, it is symbiotic. Okay, and if it is just random anywhere, then it is atactic, symbiotic, and isotactic. Next we move to the polymerization methods. Okay, polymerization techniques or methods. So in two ways we can distinguish them. One is homogeneous, other is heterogeneous. Homogeneous will make bulk bulk is homogeneous, and bulk and solution. Okay, bulk and solution. And here in heterogeneous there is suspension and emulsion. Okay, by these name we can also understand it is heterogeneous. So let's understand one by one. Okay, in bulk what we have the beaker, we put some monomer, we put some initiator, let it grow. So because this will grow and there is no impurity, that's why it is about 100% pure, but the heat control is very bad. Okay, heat control is not there. One examples are nylon is there, then polyesters and PMMA, and more such examples. Next we have solution. In solution there is again this beaker, we have monomer, initiator, but now we have a solvent as well. Now this solvent makes it less pure because it's obviously the solvent is also there, so makes it less pure. But one thing it does, it gives a good heat control. Okay, examples are in this, one way to remember is the solution. So solution is paint. So remember this by paint in pan. Pan is polyacrylonitrile, so paint in pan. So paint actually paint and pan are two examples, famous examples. Next, move on to the next is suspension. Okay, so in suspension polymerization what happens is that the monomer and initiator are added, but now we have with the monomer we have a stabilizer. Okay, we have a stabilizer, let me write it down, stabilizer. Okay, this makes it stabilize. So there are these small monomer quantity that are separated out and a suspension is created. Now we need because of these small sizes, it is about millimeter sizes, so heat control is even better than solution. Example of this is PVC. Okay, these small beads, we mix them together and make a PVC rod or pipe that you can say. Okay, this is from suspension. While emulsion, the final one, we take again the same reactor and we mix the monomer, but now monomer with soap. Okay, monomer with soap and inhibitor, initiator that initiates the polymerization with the water, that is water soluble. And now micelles would be formed because soap and water, they go separate out, so micelles will form, and they will be even less smaller particle of polymer of micrometer, but the molecular weight will be more because now more such particles would be there. It is the least pure. An example of this is you can say SBR, styrene butadiene rubber, and sometimes PVC also. Okay, let me just summarize a very important characteristic, that we have bulk, solution, then we have suspension, then we have emulsion. So size of the polymer will decrease. So let's say size of the polymer will increase from here. I'm drawing the arrows in the order of increase. This size will increase, that's most in the bulk. Then we have purity. Purity is also increasing towards the bulk. Bulk is the most pure. And finally, purity. And also, if we see the molecular weight, that is decreasing opposite. So emulsion will have the most molecular weight, highest molecular weight. Emulsion polymerization technique. Now we have the LDPE, and that is low density polyethylene, LLDPE, linear low density polyethylene, HDPE, high density polyethylene. Now the density, okay, rho that I'm telling, this would be highest in high density polyethylene. Obviously this is highest, while the pressure, so pressure will go opposite. Rho density is highest in SDPE, but pressure is highest in LDPE, about 1500 atm. In SDPE it is around 10 atm. Okay, it is, and in between it's 330 atm. Okay, now let's see the structure. LDPE, because the density is low, it occupies a bigger volume. Okay, so for that there is a lot of branching. Well, here there are less branching, but there are branching, and in there very less branches. So because of this more branching, volume will increase. We know density is mass upon volume increases, so density will decrease. That's why low density polyethylene. Okay, let's talk about the catalyst or whatever the initiator. So here LDPE, now it is more, the LDPE is more branched, so its catalyst is the opposite, it's less branch, that is H2O2 peroxide, or you can say oxygen traces. So this is less branch, while on the other hand in HDPE we have Ziegler-Natta. Ziegler-Natta is highly branched, however HDPE is very low branched. Okay, this low branch, this is one way to remember that the opposite happens. So in Ziegler-Natta it is TiCl4. Obviously you can see how much branching is there. Dot Al, aluminium, and aluminium we have C2H5 3. Okay, this is a very complex catalyst of initiator, but this is highly branched, so this is less branched. This H2O2 is very less branched, but LDPE is highly branched. One way to remember this. Okay, or for LDPE also we use Ziegler-Natta. Here we can also use Phillips catalyst some cases, and you can remember this chromo, that is chromium and molybdenum, chromo oxides. Okay, now we move to one by one. So polypropylene. From propylene, like it's from propene. You get it from propene by using the same, because polyethylene, polypropylene point kind of same. We use the Ziegler-Natta again, and we can also use the metallocene. Okay, so scene, so in this way you can remember, but mostly we use Ziegler-Natta, and then we have also we can produce it with ethene plus propene. It's just adds on. Okay, addition reaction, simple addition reaction, not much to worry about. We have next polystyrene. Styrene is very important, and from styrene we can see benzene, styrene, benzene. Okay, what we do is we take this ethene, benzene, polystyrene, in. Okay, we take the benzene and the ethene, we mix them. This goes over here, this comes here, and this becomes the main process that happens is first the alkylation happens, like this comes here, this becomes CH3, and then we remove hydrogen from here to make it styrene, and finally styrene is from by first alkylation, adding this, removing the hydrogen to dehydrogen. So alkylation and dehydrogen will finally make the styrene, which is this. Okay, styrene, benzene, ethene, styrene. Okay, and the alkylation and the hydrogenation, they are carried out by iron oxides. Okay, so this thing you need to remember, that iron oxide does this. And the main for the benzene this styrene polymerization we use, now this uses benzene, so a similar initiator is dibenzoyl. Okay, dibenzoyl peroxide. So here benzene from benzoyl, so dibenzoyl peroxide is used. Okay, so let's move on to the next, that is PVC, very important. Polyvinyl fluoride, vinyl fluoride, chloride is there, obviously Cl is there. Also we have the free radical, so for that we have this vinyl fluoride, and like the free radical will be there. Okay, so that way it will proceed. Now to use this, because we see like for vinyl fluoride, this PVC is used to mostly make like pipes. Okay, one way to remember is that bully. Okay, bullies like bully. So there are bullies which use these pipes and beat up people. So one way to remember that the initiator is bully. That means butyl lithium. Okay, so this is the initiator, bully. Okay, butyl lithium, one way to remember. And next is also we can use persulfate. So poly PP something, you want to remember it that way. Okay, because CT I think remembering is really difficult for some people. Okay, these are some methods. Okay, let's move on to the next. So we have mainly sorry addition. We have mainly addition and condensation type of polymerization. In condensation, what will happen? Something will condensate out, like water. Either water will be removed to two polymers, P1, P2 adding, and something going out, that is condensation. So water or CO2 or something else or NH3, something would come out. Addition are very basic, free radical. But now let's talk about a polymer that is through condensation, that is polycarbonate. Okay, I'm sorry for my bad writing. This is going to be the fastest video, so I have to complete really fast. Okay, so polycarbonate, that is through solution polymerization. Okay, from solution carbonate we mix this carbonate, and how it is formed, this is like we use the bisphenol A. Okay, we use the bisphenol A and plus the NaOH to form the sodium salt. So bisphenol A is something that you need to remember. So carbonate, this B carbonate, and bisphenol A, something that you can relate and remember. Okay, and in this the carbonate, so carbon something, so CO2 is exited, it comes out because it is a condensation polymer, something has to come out. Okay, next we move to thermosetting. Plastics or polymers, basically whenever you see this thermoset, it means it is set. Okay, with heating you cannot change this shape, and it is set. Okay, life is set of that polymer, you cannot change with heating. So one thing is to that remember is that always when you see one very common example, just remember that anything is set, so it is in a good form. Okay, this cricket player, let's say this cricket player is now set, well settled, set. Okay, so he is in a good form. So form, this way you can remember. And formaldehyde, so formaldehyde is something mostly in thermoset. This is not just formaldehyde, we have phenol and formaldehyde with methanol, and we have urea. These two are major examples: phenol formaldehyde, urea formaldehyde, and these are created by solution. Why solution? Urea, small tiny particles are created if you have done that in lab. So what happens? Tiny particles are created of this urea, okay, of formaldehyde. And also there is resin, okay, epoxy resin. Okay, this is also thermoset. And finally this is from the bisphenol A, again bisphenol A. Okay, just remember this resin, epoxy resin. Okay, next we have melamine, very favorite melamine. We have cutlery of all these. So what in melamine, if by chance someone asks you the structure, just draw some benzene ring, and in that benzene ring 3 alternate, put N instead of this. So melamine N. Okay, there is N here, so there is nitrogen here, 3 nitrogen, and from this 3 nitrogen. This is how it's structured it is. And melamine, it is like this. Not need to worry, go much in detail. Okay, this is just revision. And for elastomer, let's move to elastomers. So elastomers, one of the most favorite is SBR. Okay, styrene butadiene rubber. Okay, you can see it is formed by styrene and butadiene, and a rubber is formed. Okay, this is from copolymer. Okay, this is copolymerization. Or just remember that these two just add up. Okay, styrene about 20%. Okay, and rest is butadiene. This add up, and this styrene, adding styrene actually helps us to put the abrasion resistance. This is a very important property, abrasion resistance. Okay, we can have butadiene rubber also, but putting styrene, what the styrene does, it puts some good quality of resistance, abrasion resistance. Okay, this is from the free radical mechanism again, and it could be elastomers, SBR, mostly from emulsion, could be from, in some cases, solution also. SBR solution also is there, solution polymerization, both ways it is fine. Let's quickly now let's see other spandex. Spandex is made from polyurethane. Okay, polyurethane from urea and ethane. So E here, and don't know where to find the U here. But spandex is urea and ethane. We make mostly pants out of this. Okay, and jumpsuits. So like polyurethane is from spandex. That's how you can remember. Yeah, urea is related to uric acid, perhaps you can remember that way. Spandex. Okay, cyclists mostly wear that. Okay, next let's talk about fibers. So in fibers we have polyamide, we have, so let's talk about the polyamide. Amide means nitrogen, so it's nylon. Okay, so that is nylon. Let's talk about 6, that is from adipic acid, and plus the hexamethyl diacid. Okay, so these two create, and these two, and minus H2O, so water is removed. Okay, from adipic acid, and there is different carbon of 6 carbon, so hexamethyl, and that way from both we have the nylon 6. While for nylon 6, let's talk about nylon 6. We have a ring opening, and it is of carbamate. So sorry, carbamate, caprolactam. Okay, caprolactam. This is kind of a ring in which one of the elements have O. Okay, one of the elements have O, and it is not a 6 ring like that. It is kind of like this: 1 2 3 4 5 6, 1 2 3 4 5 6, and 1 2 3 4 5 6. This one more, please, one more like this: 1 2 3 4 5 6 7. Okay, and here in one part N is there near to this. So caprolactam is like this ring will open up, break from here, and it will form nylon 6. Okay, now what we have next is another fiber, that is polyester. Polyester means the polymerization of the polymer of the ester, and this is mostly in 2, Dacron and pteryline. So in Dacron, remember DMT. Okay, DMT, Dacron, DMT, dimethyl terephthalate plus ethylene glycol plus ethylene glycol, and here, so this is the main thing here. And in pteryline, and because this is PET, polyethylene terephthalate. Okay, so in Dacron, DMT plus ethylene glycol. In pteryline we have dimethyl, no, here we have dimethyl terephthalate. Here we have, what we have is terephthalate. This is, I should write it PTA, pure terephthalic acid. So this acid, and plus ethylene glycol. Dimethyl say DMT, and this is PTA, so T and T, so pure terephthalate acid plus ethylene glycol, here DMT plus ethylene glycol. Byproduct, because this is condensation polymerization, so byproduct or something that would come out here would be MEOH, while here it is water. Here it is transesterification because polyester is there, so transesterification, while this is by esterification. Okay, and the main for Dacron and terephthalate, the initiator for Dacron is like apron. So apron, so my aunt wears apron. This way is to just remember. So Dacron means apron, and my aunt wears apron, so that means it is antimony. Okay, so this the initiator is antimony. Okay, antimony trioxide, and one way to remember is Dacron, apron, and ant. Okay, and here we just use this, so T for this terylene, and we can say T for titanium oxide. We use titanium oxide. Okay, let's now move to the next part, that is the most important thing, like acrylonitrile. Okay, one of the most important, because here what we do is C3 propylene plus NH3 nitrile, so it means nitrogen is there plus NH3. Okay, propylene, NH3, and oxygen. Okay, acrylo, O and N are there, oxygen, and this acryl means this is added propylene. Okay, all the three. So amoxidation, this is NH3 ammonia, so M, and this is oxidation, so amoxidation occurs here. And finally we find acrylonitrile. The initiator is acrylonitrile is in my mobile. Okay, this way to learn is mobile means mo and bile. So this is molybdenum, bismuth. Okay, this is how you can actually remember this. Acrylonitrile is in my mobile. Okay, so mo and bile, mo, molybdenum, and bismuth. Next we move to orlon. Okay, we move to acrylic. Here we have two things, orlon and dinyl. Okay, orlon and dinyl, and this dinyl is, it's like the dye. So where we can dye, it's emulsion polymerization, so it is emulsion polymerization method, and this orlon is created by suspension polymerization. Okay, suspension, and this emulsion, like this is kind of a dye, one way to remember. Okay, not actual dye, and both use acrylonitrile. So dye, why I'm telling this dye to remember this is that emulsion polymerization has soap. Okay, so when there is some dye, we need to remember this, we use soap, so that way, but this is just a way to remember. Okay, nothing to just worry about. Acrylonitrile is used in both of these, and what we use that here L is there. Okay, here L is at the last, so one way to remember that it uses vinyl chloride. Vinyl, L is last, chloride. Okay, it uses vinyl chloride, while this one actually is acrylonitrile only. Okay, this we add vinyl chloride to get dinyl. Okay, and both these are just the monomers, while the initiator are peroxides or persulfates. Okay, persulfates, these two are used. Let's move on. Now let's finally see rayon. Okay, and the process to make rayon is very important. It is SSA, let me write down like this, SSAXRP, P not F, Sagraf. Okay, if someone says rayon, you can say it's like saffron, saxraf. Okay, this is a way to remember. First we do is steep process. What we do, we put the pulp. Okay, the pulp comes here, and to first get rayon, okay, rayon, we need to put here like a way to remember rayon. So N is the last, that means NaOH. We put first NaOH, alkaline cellulose plus NaOH, base, alkaline. Then we shred it, then we age it. Okay, then we shred it to make it fluffy. Then we age it. To age it, we give it oxygen. Okay, we give it oxygen, like a person breathing will slowly and slowly it will age. So that way you can remember that rayon takes in oxygen to age, and first alkaline like NaOH, okay, oxygen to age. So aging happens for like 2 days, 1 day, 2 day, and then xanthation. This is xanthation. In which the xanthate, the CS2 is added. Okay, this is no way to remember this. You have to remember carbon disulfide, CS2 is added, while this filter will actually give back us CS2. Okay, and also this is ripening. This is filter, xanthation, this is ripening. To ripe it, we will add some water to make to ripe it. Okay, and here also we add NaOH also again. Okay, so this is the whole process, and after that we do spinning and we get the viscose rayon also. In viscose rayon, like the ripe cellulose and the H2SO4, some acid is added, and in a tub, and here it is spinning happens, and finally ZNS is also added. So SSS, some sulfide stuff is added, and finally we get viscose rayon. Let's move to the petroleum section now. So in this, the paraffins, we have olefins. I hope this are clear, but if not clear, let me. Paraffin is like this, like a straight chain. Olefin is like bonding, okay, like a double bond. Naphthalene is like cyclic straight chain, and aromatics is like cyclic bonding. This way you can remember this. Okay, paraffin, olefin, naphthalene, and aromatics. Now next is, first let's start with API. API is measures the gravity, API gravity. This is used, and the formula is 141.5 by rho or Sg, specific gravity, minus 131.5. So what is this API of water? So Sg is 1, that means API is 10 of water. Okay, this is just a measurement, American Petroleum Institute measurement. Okay, and as API will increase, because API, if API is increasing, that means Sg is actually less, even less, so it is lighter. While API, if it is decreasing, Sg is, that means Sg, the specific gravity, is increasing. Let's talk about two processes simultaneously. Okay, one main is our petrol engine, and the other is our diesel engine. Okay, so what happens, we have piston in both of these. One operates by ignition. Petrol operates by ignition. The spark is there, and it ignites, and it pushes back the piston down here. Okay, and for this we need more of aromatics, because we need it to come up here, and because it's like this. Okay, when it comes up, this part is compressed. It's compressed, and finally it's ignited. If it is ignited well before, then this piston won't go up to that extent. It will just go here till here and then come down. So we want it to ignite, because ignition process ignite at when it is almost here. Okay, when such a low volume is there, and then the sparks is there, and it ignites. So aromatics is the best option for that, because it will help us to reach till here and then ignite. Aromatics, best option. While here, this is compression. It works on compression. Diesel engine, compression, and what will happen here, it works the other way around. When it will be compressed, so paraffin is the best, the most favored here. Okay, so here we can see we have octane number, and it's the highest of aromatics. Here we see cetane number, it is highest of paraffin. Okay, let me give the whole arranging order in the ascending order, descending order. Octane number, let's talk about octane number and cetane number. Octane number is a number that characterizes the petrol fuel, and we know this, that it's high aromatic, so there will be high octane number. It's just the N-heptane and octane. So how much proportion is there of N-heptane or octane, and if the octane is more, that means you know that everything. Okay, if octane number is more, that means less knocking would be there and a more stable engine would be there. So we will prefer higher octane number. And cetane number, so let's write there ascending order, descending order. This is paraffin, olefin, or you can even say naphthene, olefin. These are quite comparable, and aromatics. This is for octane number. Octane number of aromatics is more, and the reverse is true, like this case. So this is for cetane number. This is about 50, this is about 90. Okay, in ranges actually. So next we have one more thing, is that here these two are done. So there is one more. This is aniline point, aromatics only. Aniline is aromatic, so we can check how much aromatics is there. Okay, so what we do is take the aniline, okay, aniline, and take the fuel. Okay, both like 50 ml, like equal proportion, and we try to mix them. If they mix up well at a particular temperature, okay, there would be a temperature, we will increase the temperature to mix them well, and that temperature, when they mix them well, that is the aniline point. Okay, so if there is less aromatic, obviously at a very high temperature it will mix well. If the fuel has more aromatics, it will have a low aniline point. So less aromatic also means that it is more paraffinic. That is how we find out the aromatics, how much aromatics is there. Now in there is also like smoke point. Smoke point means tells us about the kerosene, how much smoke appears, so it mostly tells about the kerosene. Okay, there is pour point. Pour point means the point below which the fluid cannot pour easily, it will freeze out. Okay, so least temperature it will pour. Then let me talk about the other things like hydroprocessing, where hydroprocessing, two things, hydro treating and hydro treating means hydro desulfurization also comes here, and this is hydro cracking. So hydro cracking means we produce the hydrogen to crack the compound, and approximately C3 to C12 we get after cracking, and hydro treating removing the sulfur. And then we have vis breaking and coking. So vis breaking is like viscosity breaking, and we have coking. These two are of thermal cracking, okay, where high temperature, so high temperature, high pressure, thermal cracking, vis breaking and coking, that forms the coke. Okay, high coke is produced because thermally it is cracked. And this catalytic cracking, that is FCC. Okay, FCC, let me draw that. This is my reactor, let's say. Okay, FCC reactor, and this is my regenerator. So this is my reactor and this is my regenerator. Okay, so catalyst comes here, again it regenerates and pushes it back, speed goes here out, the cracked product comes out. Now what happens in the reactor? We need to do cracking in the reactor, we need to break. So it is endo, we need to provide heat to break. While for regeneration, we need to take out the coke or the carbon deposits from the catalyst. So when this will come out, it will be an exothermic reaction. This is what it means in FCC. And Now what we can do here, we have different processes. Now 4 types of processes are really main, and these are RIPA, 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 okay, RIP A for RIP, anybody, RIP Adam, sorry, okay, so RIPA. So first, this is reforming, okay, this is isomerization, this is polymerization, okay, these occur in the petroleum industry only, okay, and this is alkylation, okay. So reforming means to reform, okay, to reform, so that whatever is broken, reform it to make better product, and this is done to improve the octane number, okay. And what happens is that naphthalene actually form a higher octane number here, okay. So here the catalyst use, okay, one way to learn is that we use platinum, okay. This is a very costly process because we use platinum, okay, very costly, that's why it's the first, okay. It's the first thing in RIPA, it's the first because it's very costly, platinum. And we can also use silica alumina, non-precious, okay. Next is isomerization means two olefins, okay, you can see two olefins will combine and provide some like isoparaffin something that will be provided in this isomer. No, sorry, this one is for polymerization. That polymerization, two olefins will combine to give some isoparaffin. Polymer, two will combine olefins, okay. So this one is for polymerization, okay. Isomerization means isomer, simple isomer, like it is 2-isobutane will go to isobutane, okay. Just isomer will be created, and in this process, like n-butane to isobutane, it is a good example. N-butane to isobutane, isomer is created, okay, and paraffin is now moved to isoparaffin. Next, here in polymerization, everything is done to increase the octane number. In polymerization, we see two olefins make a polymer of paraffin, isobutane something, and P, so you can see phosphoric acid, okay. Remember P and P, phosphoric acid is the catalyst. And lastly, alkylation means make some alkyl product, that means paraffin plus olefin. So paraffin plus olefin, this olefin putting this alkyl thing with a non-alkyl thing, that is olefin, we can find out an isoparaffin, okay. And this alkylation, so one is like paraffin and olefin. So to remove this double bond, one way to remember it, we use H2SO4 or HF. So acid we use because we have to break this double bond, okay. So one way to remember is that we need an acidic condition for alkylation. Let's move on to next. Next, 3 important things are here, like, let me write down like this way: CO to H2, CO to H2, CO to N2, and C3 to C4. What is this? If it is the ratio of 1:1, 1:2, 1:2, in this there is CO2 is also there, okay, but mostly this is 1:2 like this. And this is, let me tell you about their names first. This is CONH211 water gas. So water gas like H2O, okay. So this is H2O. This way you can remember 1:1 ratio. 1:2, it's not like H2O, that way not forming. This is trick to remember. So this is syngas. Now this is N2 is more, so air is more. So this is producer gas. Producer has a lot of air, okay. So producer gas, water gas, syngas, producer gas, and this is natural gas, okay. propane and butane. Now the order of calorific value is like natural gas the most, then water gas, then syngas, and then finally syngas more, then water gas, and finally producer gas. Producer gas less because it has more of nitrogen inert in it, less calorific value. Now let's quickly see CO plus 2H2. Okay, CO plus 2H2 and with CO, okay, like CO cobalt, okay, CO, this will make CH3OH with methanol. Okay, this is syngas to methanol. This is for one reactor, and CO, that's how you will remember. Second is formaldehyde, how we get, so you have methanol, this is methanol, and so formaldehyde is a very cheap product is cheap, but the catalyst is very AG, very costly. AG means silver. Okay, catalyst is called costly, but product is cheap because methanol, you can see it's very cheap. So this is way to remember, for cheap product you need very costly catalyst. Okay, methanol to formaldehyde this way. Okay, next vinyl chloride. Vinyl chloride means this ethene plus chlorine is like vinyl chloride. CH, I should write CHC2. So this way C2 something H into Cl. Okay, and H for this, because we need chlorine, so that is comes from FeCl3, iron chloride. Next is this, let me write down my cumene. So cumene is produced by producing C3. Okay, C for cumene, C for C3 is 3 here, and adding benzene. Okay, finally we add benzene, so it will be like this kind of thing. And finally, now this adding of benzene, so cumene, we need zeolite. Okay, light, mean, you are very mean, so don't take it like lightly. This is how where you can remember. So cumene, then if you add some oxygen like peroxide here, you can actually get phenol also. So cumene to phenol, and acetone will be the byproduct, but cumene to phenol could also be obtained. Next, I have told you acrylonitrile. Let's take oxo process. Oxo process is in which oxo, okay, that means oxidation is there. So you O for olefin, we take any olefin, then O, so we have CO, O here, and because CO is there, so we put syngas. Okay, and this again CO, so CO, that is cobalt. Okay, ruthenium is also there, but cobalt you can easily remember. CO here, O. Okay, oxo process is hydroformylation. So what it will produce is your aldehyde, like HCHO. So aldehyde it will produce. Okay, and aldehyde can be converted to alcohol by adding hydrogen. Now let's see how benzene. To produce benzene, we have this. What is this? Toluene. Toluene to benzene is very simple. Just remove this C. Okay, how to remove this C? With the help of PCM. This is not physics chemistry maths. This is platinum, chromium, and molybdenum. This is the catalyst. Okay, to make benzene you need to learn PCM. One way to remember that. Let's make phenol from toluene. Okay, we have toluene, and toluene to phenol is a redox process, because first you need to oxidize this. Okay, first oxidize this. How you will oxidize this? You will make it to benzene. Let me not make it the structure here. Let me write down. From toluene oxidize, so you will get benzyl peroxide. And for this oxidation, okay, this is oxidation, and then from here, from this, to make the phenol, you need to reduction. Okay, reduction minus H2. H2. So this will reduce it, and H will come here. First putting the O, then H. Okay, and for this you LiAlH4 is the best for reduction. Next, phenol from benzene. So benzene, from benzene, first add Cl2 in FeCl 3 ClCl, okay, and then we will get benzene chloride, okay. Then this benzene chloride plus NaOH, so that we can get the OH for phenol, but this will create sodium benzoate, sodium with benzene will be there. And finally this sodium benzene, we need to remove this sodium. So what we'll do, because we add a base, so we add HCl, so that H takes place of this Na sodium, and finally we get phenol. So we use first chlorine, then chlorine replacing with NaOH, then finally again HCl to remove this Na. This is the whole process. This is first chlorination, then causticizing, chlorination, causticizing, and finally hydrolysis, CCH, benzene to phenol. Lastly, let's look at just for now, I think phthalic I remember, phthalic anhydride. For phthalic anhydride, you take O-xylene, okay, O-xylene, oxygen, add oxygen, and oxygen is added, so V2O5, O5 here, oxygen also added, so phthalic anhydride. Or you can take naphthalene, okay, xylene, lean, and oxidize, and again V2O5. Same ways malic anhydride, that this could be the malic is benzene. So from benzene, the malic is benzene. Of everything, malic is benzene. Malic means God. So of all PCM, the chemistry God is benzene. So add benzene with oxygen. This is how you can remember. Again oxygen for anhydride. Anhydride, just remember, you need to add oxygen. Anhydride, okay, oxygen. Adding oxygen, we get again V2O5, we get malic anhydride. We can also get malic anhydride from N-butane. So N-butane, we can get malic anhydride by oxidation. So these are where the whole everything. We can also prepare methanol from NH3, okay. Just remember this is possible, okay. This is also a process, okay. I'm not going into detail, but this is also possible, okay. So I hope all these things helped you. Please like, share, and subscribe if you really want such videos, so that we can quickly cover everything rather than watching the 1 hour 2 hour long videos. Thank you guys.